Hello and welcome to today's lesson on magnets and magnetic fields. Today we're going to be describing the attraction and repulsion between like and unlike poles of a permanent magnet. We'll also describe the difference between a permanent magnet and an induced magnet. We'll describe how magnetic fields of a magnet show the strength and direction of the magnetic force, and we'll explain the behaviour of a magnetic compass. Here is an activity that you can take part in at home if you'd like to. All you'll need is a paper clip, a piece of thread, some blue tack and some kind of magnet. What you're trying to do is make the magnet float in the air. If you manage to do that, you can also experiment by putting different objects such as a piece of card between the magnet and the paper clip. Here you can see the setup for the experiment. All you have to do is hold the magnet above the paper clip with the paper clip securely tied to the thread, which is secured to the table with the blue tack, and the paperclip will seem to levitate. Experiment by putting different objects between the magnet and the paperclip and see what happens. You probably already know that the opposite poles of a magnet will attract each other, so a north pole and a south pole will be pulled towards each other, whereas the north pole and a north pole of the magnet, the like poles, will repel each other and will move apart. We can explain the movement of the magnets using magnetic field lines, and field lines go from the north end of the magnet to the south end of the magnet, and the magnet will always move in a way that will allow these field lines to become shorter. One way to visualise field lines is to use iron filings. If we shake iron filings over a bar magnet, then the little iron filings will all line up in the direction of the field lines. Field lines represent something called magnetic flux. The number of field lines or flux lines passing through a particular area is called the magnetic flux density, which is also the same thing as magnetic field strength. Field lines go in and out at the ends of the bar magnet. They are closest together at this point, and so the density of the field lines gives you an indication of the strength of the magnetic field. This is why at the ends of the bar magnet you feel the strongest force of attraction. In our previous experiment, the bar magnet is what's called a permanent magnet. The paperclip, on the other hand, is not magnetic, but when it was brought into the magnetic field of the bar magnet, it became what's called an induced magnet. We can explain how something can become an induced magnet by using the domain model of magnetism. In the domain model of magnetism, materials like iron and steel are made up of tiny little regions or domains, and each of these domains acts like a mini magnet. When you put it in the magnetic field, elements of it start to line up. The stronger the magnetic field, the stronger the induced magnet. And now we've got some questions for you. You can choose between either the left-hand side, which are the normal level questions, or the right-hand side, which are extension questions, which should challenge you just that little bit more. Pause the video now and work through at least one side of the questions. And here we've got the answers. So pause the video now and work through these, marking your work, and if you need to, make any corrections as you're going through. In the answer to question 3, we discussed how the Earth behaves like a bar magnet with its own magnetic field. But which way round would the bar magnet be in Earth? Rather confusingly, the north pole of Earth behaves like the south pole of a magnet. This is because on a bar magnet, the north pole is a north-seeking pole and the south pole is a south-seeking pole. So to summarise, if a magnet is allowed to spin freely, it will naturally come to face in the direction of the North Pole. A compass uses this phenomena to allow us to find north, and a north pole of a bar magnet should be called a north-seeking pole. I'd now like you to write a short paragraph in your books to explain why the north on a compass should really be called the north-seeking pole. Pause the video while you do it. And here is an example of the explanation you may have given. There are 4 key points here, so go through your work and check that all 4 of these are present in your answer, and if they're not, add them in. I'd now like you to sketch the Earth as a bar magnet with its magnetic fields around it. Remember that the field lines go from north to south, and so they will go from the bottom of the Earth to the top. Your answer should look something like this. Don't forget to include the arrows. If you'd like to, you can make your own compass by rubbing a magnet in the same direction across a needle. This will cause the needle to become a permanent magnet. This is because the individual domains each line up in the direction of the magnetic field as the magnet is drawn across it. Eventually, the needle becomes a permanent magnet itself. Then all you need to do is place the needle on an object that will float, such as a piece of cork, and place it in a bowl of water. And then you should see the needle spin around and point in the direction of north. Finally, what do you think would happen to a compass if you took it exactly to the North Pole? Pause the video and try and write an answer in your book. First of all, the needle will try to point downwards, but because the compass won't allow it to move in that direction, it will just point in a random direction, although it may spin if it was set in motion. Well, that brings us to the end of today's lesson. Thank you very much, and I hope you found it useful.